In chapter 17, we're going to be paying attention to the alpha carbon on our carbonyl compounds, both aldehydes and ketones from chapter 16 and carboxylic acids and derivatives from chapter 15. Because on this carbon that's adjacent to our carbonyl, we have a whole second site of reactivity that we didn't discuss in chapter 15 and 16. Those earlier chapters, we just looked at a nucleophile coming in and attacking the carbonyl carbon, which it certainly can do. Right? We can do a nucleophilic acyl substitution. That's what a lot of chapter 15 was about. We can do a nucleophilic addition or an addition elimination like we saw in chapter 16. But a base can also come in and pull a proton off of the alpha carbon itself. And that extra acidity that we have at the alpha carbon changes a lot of the reactivity that we might expect. So the question we need to think about first is, why is that hydrogen acidic? Because we've never considered hydrogens on sp3 carbons to be acidic. They typically have a pKa higher than 60. It's a relatively non-polar bond between carbon and hydrogen. Right? So we have no reason to think that it's acidic, especially when we're sp3 hybridized. We know as we go to sp2 and then sp, we can get more acidic. But here we're still looking at sp3 hybridization. So why is this hydrogen on the alpha carbon of a carbonyl compound in fact acidic? And that lower pKa value, you see here a range of 16 to 20 on aldehydes and ketones and 25 on esters. Why are they so much lower than that 60 that we saw before? Well, that alpha carbon, right, obviously must be acidic based on the acidity-basicity principles we've always been discussing, right? It must have a more stable conjugate base. And I hope you're already thinking, all right, it must have something to do with that carbonyl. And in fact, that it does. We do have one definition down there at the bottom. If we have something that has an acidic hydrogen on an sp3 carbon, which we have in this situation, that's called a carbon acid. In this next table, table 17.1 from your textbook, has examples of a lot of carbon acids. You see lower pKa's here for hydrogens that are bonded to sp3 carbons. So let's get into that business. Why is it? Well, previously, if it's just an sp3 hybridized carbon, nothing else is going on. If I'm to deprotonate that compound, the electrons that are left behind go directly onto carbon. They're localized onto an element that's not electronegative, right? Carbon doesn't like to be a carbanion like that. But here, with the alpha carbon on my carbonyls, when I deprotonate in the alpha position, those lone pair electrons that are left behind get delocalized, right, throughout this system. And we've seen several times now, delocalization increases stability. And in fact, not only are they delocalized in this pi system here, but they get delocalized onto oxygen, which is inherently electronegative and happier to accommodate those electrons than carbon was, right? So two factors that are increasing the acidity at this position. Even though it's an sp3 hybridized carbon, right, it's acidic because those electrons that are left behind are delocalized and oxygen's happy to accept them. But the next question we need to think about is, why were aldehydes and ketones more acidic than esters? Okay, those aldehydes and ketones, 16 to 20, esters about 25. Okay. And the reason for that is when we have an ester, we have some competition. Okay. Here, this is showing deprotonation in the, over here, deprotonation in the alpha position, right? But we compete with electrons being delocalized from the ester itself. Okay? So notice there's two different contributors on the left and the right side there. So because of that competition, right, it's less readily able to bear that electron pair. So esters are less acidic than aldehydes and ketones are. And we have other things that can form carbon acids as well, right, with a nitro group or a nitrile, okay, or with an amide. As long as we have the ability to delocalize the electrons that get left behind in the alpha position, something will serve as a carbon acid. Okay? In all three of these situations, we get delocalized onto an electronegative atom. And if we have two groups that we can delocalize onto, we get even more acidic. Okay, so if we have a beta diketone or a beta ketoester, these compounds over here, right? So we've got in one position and then another carbonyl in the beta position. That's what beta comes from here. That alpha carbon that's between the two of them, right, is incredibly acidic. Notice how low these values are now, 8.9, 10.7. These are even more acidic than just having an aldehyde or a ketone or an ester, because those electrons that get left behind can be delocalized two ways now onto two different oxygens. That's shown right here. Okay, deprotonate, I can delocalize to my left, I can delocalize to my right. Okay, so that gives me a lot of electron density on my oxygens up top and gives me an incredibly acidic hydrogen there in the middle. So we're going to use those ideas to think about a couple of reactions. That's what a lot of this chapter is about. Starting first by jumping back 10 chapters to something we first introduced in chapter 7, okay? The idea of ketones and enols, and specifically keto-enol tautomerization. And if you recall from chapter 7, tautomers, the keto tautomer and the enol tautomer here, differ in the location of their pi bond and a hydrogen. Right? From the keto to the enol, our hydrogen moves up, our pi bond has moved down. And in most situations, we said the keto tautomer was more stable than the enol. Okay, we saw that tautomerization back in chapter 7. And notice the difference there, 99.9 to 0.1%. But now that we've got this idea of diketones to think about, one thing you should have on your radar is that hydrogen bonding can stabilize an enol tautomer, right, in one of those positions, right? Hydrogen bonding there between the carbonyl, oxygen, and that hydrogen. So that changes our ratio from 99.9.1 to 85.15, makes the enol tautomer much more stable, okay, but the keto tautomer still predominates. The one situation we're going to be looking out for immediately is phenol. With phenol over here, the enol tautomer is actually more stable and predominates because in the enol, we've established aromaticity, right? That aromatic pi bond there in benzene. Okay, so know that for sure, right? Aromaticity trumps everything. If there's a way that we can get something to be aromatic, it will always be more stable, which is why the enol tautomer dominates in this situation. Okay. So now knowing that and knowing what we know about the alpha carbon, we're going to think about that conversion again, tautomerization, which can be acid or base catalyzed. And then we'll see how some other things in the pot can change the substituents we can put at the alpha carbon. Okay. These are things we've seen before in chapter 7, okay? But you can get them in your notes again. It's probably been a while. So the keto tautomer, right? How does that become the enol? Here we see it being base catalyzed, this tautomerization. Okay. Our hydroxide pulls a proton, right, off of the alpha position, which should make a lot more sense now, right? Previously, we hadn't discussed why this is acidic. Right? That forms an enolate anion right here, right? Different resonance contributor, and then we protonate our oxygen, we formed the enol. That's base catalyzed. How about acid catalyzed? Well, we can do that by protonating the carbonyl. Okay. Then water comes in, pulls hydrogen off of our alpha carbon, and we form the enol tautomer. But that tautomerization, keto-enol interconversion, what it's calling it up here, right, can be altered in the presence of other species. And that's what we're thinking about, these kind of reactions in chapter 17. Okay. This shows acid catalyzed halogenation of the alpha carbon. This is known as an alpha substitution reaction. We took a hydrogen in the alpha position and substituted it for something else, an alpha substitution reaction. Okay. These can be acid or base catalyzed, and effectively you're using bromine, chlorine, or iodine to replace one or more alpha hydrogens when you have a carbonyl compound. So what does that mechanism look like? Well, the good news is it's pretty much the exact same as the tautomerization, right? The enolization part. Okay? Looking at the acid catalyzed first, I protonate my carbonyl. Okay? Water pulls off a proton in the alpha position to form my enol. Okay? But then that enol reacts with the halogen. It's electrophilic, right? I kick my pi bond, reform this one. This pi density picks up a bromine. Okay? Deprotonate the carbonyl, and I formed my substituted product. So very similar mechanism, just a different electrophile that's been introduced down here. Base catalyzed, we can do it as well. Okay? Sorry, base promoted, I actually should say. The hydroxide ion is not acting as a catalyst because it's not regenerated. Notice it goes from hydroxide to H2O, so it's a promoted reaction, not catalyzed. Okay, how does it work? Hydroxide pulls a proton off of the alpha position for my enolate ion over here, kicks back down, right? Same exact thing we saw before, just nothing left to protonate. But notice the difference. If I have something that's base promoted, I switch all of my alpha hydrogens for the halogen. All of the alpha hydrogens are substituted for the halogen. Whereas over here, when I was acid catalyzed, I only did it once. And that's a key idea to take away from this video for these reactions. Okay. So why the difference? Yeah. Those halogens are electronegative, right? So they're electron withdrawing. They're pulling electron density away. So after we've done the reaction one time, okay, it increases the acidity of our alpha hydrogens. So if we're base catalyzed, it's going to make them even easier to pull off. Okay? But they're also decreasing the basicity of the carbonyl oxygen, which is making that protonation step less favorable. So it's all about the first step, jumping backward again, right? Here, if it's acid catalyzed, it makes this first step more difficult, which is why for an acid catalyzed alpha substitution with a halogen, we only do it once. Okay? But it makes the deprotonation here easier, which is why we replace all of those alpha hydrogens. Okay. Last thing we'll think about in this video is carboxylic acids, okay? And trying to substitute at the alpha position here. Those aren't as easy to do because I've got an acidic hydrogen over here on my carboxylic acid as well, right? So I can't just do a quick alpha substitution like before. I need special conditions. And those are achieved in the Hell-Volhard-Zielinski, also known as just the HVZ, another named reaction. Okay. That uses PBr3 and Br2, and then a water workup to replace a single alpha hydrogen of a carboxylic acid with bromine. How does that work? Well, first, it converts our carboxylic acid to an acyl bromide. That acyl bromide is in equilibrium with the enol form. Okay? And then when we're in the enol form, look, that should look similar. Kick that down, bump over, right? Form this species over here. Water takes me back to the keto form, which in this situation is the alpha brominated carboxylic acid. Hydrolyze it back. Easy stuff. Now, once I've done that, an alpha substitution in the previous condition or using the HVZ reaction, these have synthetic utility if I want to replace something in the alpha position with a weak base. I can do that. Okay. I can't use a strong base because remember from chapter 9 and 10, strong bases favor elimination, which would put a pi bond in this situation, right? Because it's conjugated with the other, forms a conjugated system there. So if I've got a halogen in the alpha position, I can only replace it with a weak base. Next, we'll look at situations where we need to form an enolate ion specifically, but we'll save that for video 2.